everyone. I'm going to present my project that I did throughout this summer internship on DIGI2, named Graphs for Collaborative Robotics, Flexible Task Simulation and Control. In the modern factory, collaborative robots have been used to work together with humans, and most of the tasks performed by these robots can be discretized in granular operations, facilitating the planning process of a task and allowing for the exploitation of joining simple commands instead of programming complex ones. Given this, this project aims to simulate the completion of a task by a robot, a human, or both, generating a graph of operations. This graph should be generated automatically and encapsulates the different operation sequences that can be performed, having as input a series of parameters of the process. But why graphs? A graph is a structure composed of nodes and edges that relate those nodes to each other. In the context of this project, the nodes represent a task, which is divided into more specific subtasks, which in turn are divided into a set of granular operations. And the edges define the sequence between two operations or the division of a task into subtasks. For example, in this graph, the task is to build a roller with 2 wheels and 2 discs. And for that, we need to bring and mount all of them. That is more specifically to pick and place them in certain positions. Each node should be composed by attributes such as its identifier, its type, task, subtask, or operation, its state, that is, the node can be still to be done, being done, or already finished. Each state is represented by a color, to do by gray, doing by yellow, and then by green. Other attributes are the operation itself, for example, pick, and the object wheel. Tasks and subtasks should also have its sequence, that is parallel or sequential, that define if its children nodes, that is its operations, can be done in any order or not, respectively. The operation nodes should also have the actor who performed the operation and the estimated and actual performance time. For this project, 2 modular furniture construction cases were studied, more specifically the construction of a table and a chair. At the left, we have the example of a table with 4 legs, 1 base, and 8 brackets. And at the right, we have its graph with the subtasks for bringing the materials, building the 4 legs, the base, and at the end for assembling everything. For this chair is almost the same. We have the building of a small table below, and we just need to add its back. So the graphs are almost the same. We just need to add basically 2 subtasks. With these 2 examples, we can see that the potential of a graph for better understanding and planning of the process of a task, being easy to use the subtasks and sets of operations for different tasks. I also need to highlight that some operations cannot be done by the robots. For example, operations involving fastening screws that are represented by yellow in these graphs, and even in fully automatic simulations that is only done by robots, these operations must be done by humans. So, as I mentioned at the beginning, the program needs some inputs for the process. such as the bill of materials, that is a list identifying all materials and components required to construct a product, as well as instructions for the process. We also need the initial object's pose and the final pose, that is the pose which the objects must be placed by the robot at the end. We also need the automation mode, fully automatic or fully manual. As I said before, fully automatic, the tasks should be done only by the robot, and fully manual only by the human. The operator's expertise, beginner, intermediate, or expert, this influences the time he needs to perform an operation and the probability of failing one. And last but not least, the graph in a JSON file with the tasks, subtasks, and operations, its attributes, and the edges. Here you can see the implemented graph. Here is doing a subtask. In yellow, as I said, are the tasks, the operations that are being done. And yeah, so for this simulation, the program randomly chooses a subtask to be performed, and its operation starts sequentially to be triggered, moving to the doing state. So in each operation that is triggered, if the actor is the robot, it sends the command and the position to which the robot must move to the UR5 API. The API connects with the robot. In each case, I used a simulator of a robotic arm because I was already on Erasmus and I wasn't able to connect to the robotic arm that was on the lab. Okay, after sending the command to the robot, it waits for it to finish and moves the node to the done state. If an operation is not successful, the operation is redone, continuing on the doing state until successful. All the simulation's failures can be seen in the final simulation log file. Whenever there is an actor exchange between two consecutive operations, a time delay must be added in order to approximate with the real interaction in the real world. And this visualization of this time delay is represented by a node called wait, having as attribute the delay time in seconds. After the simulation, there are some outputs. The task is completed by the actor. The graph in the JSON file is updated with its attributes and new nodes or wherever, and a log file. There is a text file with the title of the simulation mode, automatic, manual, the total process time in seconds, number of operations performed by each actor, time of activity of each actor, sequence of operations and its duration time, and the failures. As you can see here, on the two error lines, the operator tried to fasten a screw 2 times, and only on the third try was successful. There are also implemented some utility functions to get some nodes attributes or set node attributes specifically for the sequential and parallel nodes. The technologies used were Python, Matplotlib, and NetworkX that I've never worked before, so it was challenging to understand this technology. And Python was for develop the program itself, and Matplotlib and NetworkX for creating and manipulating and visualizing the graphs. For future work, for future work, it is programmed to add a mixed simulation besides the fully automatic and fully manual to dynamically generate and update a graph that allows two actors, robot, or human robot, to collaborate together in the same task, and when adapting to the choices and mistakes of the other, simulating the execution of all the logical paths of the collaborative process. I can also do the graph intelligence, which means the use of artificial intelligence methods on top of the graph in order to teach the agents which node to trigger or add according to the behavior of the second actor. Thank you for the attention. Thank you everyone for helping me throughout this month and making this internship a really nice internship. And thank you for Liliana especially.